record. Okay. So again, this is your roller coaster in 2D portion of the lab, and you'll get your position versus time graph going with your X position and in your Y position once you're done with the X one. Oh, and now it doesn't want to load properly. But it's the same idea as the X position one. And you'll take your data in increments of 0.5 seconds, and then you will plot that. And so again, you can add columns or erase these ones. It doesn't really matter. I would probably just insert columns. So I would say Y position in meters again, and then just putting in your numbers. Same thing as last time. I'm just gonna put some in real quick. 12, I don't know, 19, 25. Sure. And then, so we can plot this all in one graph, but we don't have to. So just remember that. See, it can get kind of messy really quickly, but you could also just do separate graphs. That's totally fine too. And again, you want to do a linear fit. And so this is what they'll look like, something like that, okay? It won't look exactly like this because your data is going to be different, okay? So don't worry about that. Let's see if it tells you how many to do. Oh, just in 0.5 seconds. So if I'm actually doing this, my Y position is going to look a little different, right? So if I take this out and I start over, if you notice, we go up in the Y and then we go down in the Y. So this is what our graph is going to look like. It might look a little bit different. It's going to go up and then it's going to go back down. So we're going to see something more along that looks like this when we're graphing. So just watch out for that. It may not exactly be linear. Okay, so let's see. If we did, let me show you an example. So if I did this and I say I want to start about there, I'm just going to set that at 0 meters just for the heck of it, because I can do that. And then I'm going to move this and restart it. So my first position is 0. Then I wait 0.5 seconds right there. And I read that it's about 8 meters now. So I say, okay, this is 8 meters at 0.5 seconds. And then I go for another 0.5 seconds so that it's at 1 second. Boom, right there. And I take my next measurement. It's about 18. And I keep going. And then if I'm at my 3 seconds already, okay, notice that I start to come back down in numbers. So at 3 seconds, I'm now at 11 again. So it gets to some peak up here. So say that's, oh, that's not 18. Sorry, I misread that. That would be 13? About 13. Because that peak, it looks like it's almost 15 or so, maybe 16, okay, where that train will hit, or not train, roller coaster. Sorry, it looks like a train to me. And then it goes back down to 11. So this is more like what you're going to see. So let me say 16, and then let me go to, I don't know, what was it? 11. And again, I skipped a couple. But notice how my curve is no longer linear, right? We've got points here and it starts to go back down. So instead of doing a linear fit now, I'm going to do, let's see, probably do a square. Nope, not a square. Let me see. Quadratic? Quadratic, okay. It looked the same to me. So, okay, so we can use a quadratic to look at the second one. So when you're looking at the y position, you can use your quadratic formula to describe the motion. Okay, so that's what's going to be a little bit different between your x and y motion, or your vertical and horizontal motion. Okay, and then from there you can look at your curves here. Okay, decide what they mean. Hopefully from last time or last lab we remember a little bit. And then it asks you a few questions about the motion, about the horizontal and vertical components. And again, that might be a little different from what's in here. See, I have 7 questions and they have 4, but I wanted to really try to break it down so that it made sense. Okay, so that's the first one. That's the first part of the lab. Now the second part of the lab is the 3 views of the projectile ball. So that's this one. Okay, so again, you're going to be taking data. Okay, the first one, you're going to make a graph of the horizontal position. And so that is just looking at this here. Either that or this one. Actually, this one would probably be easier, this top view one. So I'm going to go ahead and get my ruler. And actually it's starting where she is, and then a timer. So let me move this for a second. Let me get that out of here. Let's just watch what it does. So there's 3 different views. Okay, and so as she throws it, you can see from different positions what's going on. Okay, so her horizontal motion is easily seen here. Go away. It's easily seen here. Okay, her vertical position can be seen here or here. Okay, and so you can use whichever one works for you. It doesn't matter for the vertical. Probably be easier doing it over here if I get my little ruler out. If I just put it here, I can just do it this way, but it's up to you. But anyway, so you're going to take down your data, your information with your time as well. So you just do one at a time. And you want to make your graphs. So like last time, but now it's with a ball in air. Okay, so you'll make your graph and then insert it over there. And then you'll describe the motion of the ball for your horizontal and then your vertical. Okay, so you'll just say, you know, which way is it moving? Is it slowing down? Is it speeding up? What is it doing in general? Okay, so it's kind of a generalized question. Okay. And then it will eventually ask you to make a velocity versus time graph for the vertical motion. Okay, so not the horizontal, but for the vertical. And then you'll also describe your acceleration of that ball using that graph. Okay, so again, you can add column, and you can do it all in one graph, or you can do 3 separate ones, as long as they're all 3 there. Probably be easier to do 3 separate ones. Yes, so let's see. Are there any questions about that so far? I know that was kind of a lot. Let me see if there's any in the chat. Nope. Okay. Well then, I'll move on. When you are finding your velocity, you're going to have to do a little bit of a calculation, but it's not going to be too bad. So if you have one point that's at 0 meters, sorry, if I'm doing my vertical position, and then, my, and I have, let's see, it moved from 0 meters to 1 meter to 3 meters, and this is my time in seconds. 0, then 0.5, and then 1. my velocity in the y, meters per second, is going to be calculated based on this. So what I will do is say from this point to this point, what is my velocity? So I'm going to go velocity equals, oh, I can't write that in there. Okay. Can I write anything? Rude. Let me see if I can get this. No. This here. Okay. Oh, now my pen doesn't want to work. Come on. Okay. Well, let's see. My velocity would equal my first point in the position. So, or actually my second, my final minus my initial, right? So it would be 1 meter minus 0 meters. Whoops. And that's going to be divided by my time difference. So my time difference is going to be that 0.5 seconds minus 0 seconds. And so that's how I would need to calculate my velocities. Okay. So we would say 1 divided by 0.5. That would be, I think, 2. Oh, what the heck did I just do? 2 meters per second, I believe. Don't quote me on that. Can't do math very well in my head. Okay. Let's see if there is another way to do this. I feel like there might be. So if I'm looking at this, let's see. I'm going to start this over until she releases the ball, which is right there. I don't know if you can really tell on your screen, but this is where she barely releases the ball. I'm going to have my timer out. Oh no, I did that wrong. Okay. So if I'm saying this is my 0, I can say it's at position, what, 1.5. So I'm going to go ahead and write this down, 1.5 at 0. Ignore the first line. And then I continue. Okay. And I'm going to say at 0.15 seconds, it is at position 2.1. And let's see if I can get this. So let's see. Vertical position, oops, minus 2.1. Okay, so then I would say that is 4 meters per second, doing my calculation here. So my vertical position, my final position minus my initial position divided by my change in time here. Okay. And so I can continue to do that. It looks like that is my final there. Let's see. Let me go back a bit. Go here. And then, so you continue taking the velocities up until it reaches that maximum. And notice as I increase the time or decrease the time, that ball is still sitting there because our velocity in our y is now 0. Remember, we've been talking about that in projectile motion, where our velocity in our y becomes 0 at that peak. So that's what we're seeing in real time here. Okay. All right, so that's the basic idea of this one. And so out of all of that, you'll come up with 3 different graphs. Or I'm sorry, yeah, 3. and then put those in here, and then you'll talk about your accelerations, or your acceleration with your y. Okay, so let's see. Our third activity is this one. And it's kind of interesting. So this is where you're looking at relative motion, okay? And we didn't talk too much about it, but I thought this would be like a really cool example of it. So what we're going to be looking at here is a drone moving, and we're also going to see someone walk across the screen, so or across the grass here. And you'll be able to understand the relative motion, okay, and what that means. So I'm going to go ahead and press play. And so our drone looks like we are moving in this direction, right? And that person is moving straight forward, right? You can tell from that line that she's walking. She's walking on a straight line, but it almost looks like she's moving diagonal if we were stationary, right? So this is just the idea of relative motion. Okay, so our motion relative to their motion relative to the ground, and all of that good stuff. So that's what you'll be talking about and looking at with these questions. Okay. And then you will look at a representation of her velocity, see which one works. Okay. Let's see what else is there. Okay, and then you'll measure her velocity to the ground, which is that going to be for this one? So what you can do is make little points, and you'll say when she's at this, where are you going? Can't I move you? What in the world? I guess not. Okay, so the first one where it asks her velocity, what you can do is really just get a stopwatch here. And I believe it says, yeah, it says that these grid lines are 5 meters. Okay, so what I will do is when I'm watching this, I will start here where she's just about to cross that first line. And then I'll reset my timer here. And I'll say, okay, she's going to walk these 5 meters, and then I'm going to stop it and find that time. So then I can calculate my velocity. Okay. So she just went 5 meters, and that took 2.9 seconds. Okay, so then I would obviously divide and get my velocity for her relative to the ground again. Okay. So that's what my first step would be. I could say the velocity then is that 5 meters divided by that, is it 2.9? Yeah, 2.9 seconds. Okay, and then you get your velocity, right? In the next one, you're going to measure the velocity of the drone. So that's when this little dot comes into play. So let's see, where do I start getting to that point? Okay, so perfect. I'm right on one of these squares. And so I'm going to start my clock over and press play. And then right about there, whoops, is where I would be one full square. Okay, so the drone now has moved one full square, or 5 meters. So I'd do the same thing. I'd say my velocity is 5 meters divided by my 3.5 seconds, and then you get some answer. Okay, so that's your velocity of the drone with the reference frame of the ground. Okay. And then using those two, you can calculate the velocity of that girl if measured from the reference frame of the drone. And that's going to be based on your interpretation here in number 3. Okay. So you'll find a relation between all of these vectors, and you can show it graphically as well. So that'll be one of these. Okay. So that is looking at all of that. And then you will lock your answer and continue to the next part. And that's where it says, let me see, what does it say here? Then it'll actually, no, it'll tell you how to measure her velocity from that reference frame of the drone. Okay, so let's see. Okay, it wants you to figure it out. So I guess I won't give that away. And then it tells you to compare your measurement. So you may have to use all of these tools. Let's see. What does that tool do? Okay, it just shows you the velocity. You may need to use this one. What angle is she at? That might help. Okay, there's also your timer and your little point here that you can't move. Okay, so this one has a few tools that you can use. I would say that you will probably need to use this. Okay, you might need to use some trig to figure out that velocity, right? Because her velocity is not a straight line when we're looking at it. It looks like she's going diagonally, right? So we're gonna have to use some kind of trig to figure that out. And so then you can compare that to your value that you calculated up here, and it'll probably be pretty close. Okay? So that is the entire lab. If there's any questions, you can always let me know. But I'll have this up on Canvas as well. Let me show you guys where I put that, because I didn't quite put that in. Oh, that's not my Canvas, it's a different one. Let me see, where is your guys' class? Right here. Nope, that's not it. It's the same one I just pulled up. Okay. So this is your guys' class. Right down here on the left side where it has all these different things like your home page, your modules and all that, there's one that's called Pages. And so you'll go there, and this one I don't even know what that is. But this one right here, it says Recitation. Should be able to go to it like this. And so I will be just uploading them back to back up here on this page. So the first one's already up, that was from last week. And then today's, once it's already done and finished uploading to YouTube, which takes forever, I will have it up here, and then you can just click the link and it'll take you to that page. And I also have where you can look at my Google Notes or my OneNote that's on my computer that I do with you guys. So this is actually from all of my lecturing too, the examples and such, okay? So you can always look at these, but notice I have the recitation 9/2. So that was last week's. And it'll load, and I'm pretty sure you shouldn't be able to edit it. If you can, please don't. That way other people, don't get all confused by that. But yeah, so this will have like examples and such in it. And see, this is what I just had on there a minute ago. So I guess it updates live. I wasn't sure about that, but so you can see all of those things now. And it just pulls it up into your browser. So it's not like you have to download anything. I just wanted to show you guys that because I didn't really go over that because I wasn't sure what I was going to do with this yet. But here we go. This is our page of recitation notes. So I'll just continue to upload them here. Okay. All right. So does anyone have any questions in terms of the homework? Is there anything specific that you want me to look at? Let's see. Is there anything particular like maybe the what's it called? I can't think of what they're called. Free body diagrams or anything like that? I know they're kind of weird to look at the first time. I can tell you that one of these, let me see, this one is very similar to the example I did in class. So that's good to know. Number 10. It's going to be very similar to, let me show you guys. Might as well. It's going to be very similar to this one here, this traffic light one. A lot of these are repetitive once you get the hang of it, kind of like with the projectile motion ones last week. They can be pretty repetitive once you get it down, but it takes a while. I haven't done these in a long time, and it did throw me for a minute. I was like, wait, what do I have to do? So it takes some thinking, but once you get a hang of it, they're pretty repetitive, I should say.
Could you go over question 11?
11?
Yes.
Okay. Okay, let's see how well we can do. Okay, let me see if I can get this pen to work. Draw. Don't know why. Give me a second here. Give me a couple seconds here. My pen doesn't want to work. Where'd it go? There it is. Doesn't like me. Well, I guess I'm gonna have to use my finger, and that's gonna suck. Okay, so let's get this out of the way. Give me just a second here, sorry. Ooh, don't do that. Okay, Why does that work like that? I don't know. Okay, let's see. Okay, so we are looking at a fireworks shell, it looks like, that is fired straight up from a mortar and reaches a height of 110 meters. Okay, so our first step is always going to be to draw something because it's really helpful, I think, because then you know what you're looking at. Okay, so if we have something, okay, we're going to draw a box then. And it goes straight up. This is terrible. Oh, it's too thin, that's why. And reaches some height. H, come on, pen, equals 110 meters. Bear with me, guys, sorry. Okay, and we have some mass, 2.5 kilograms. We want to, okay, first neglect air resistance. We want to calculate the shell's velocity when it's leaving. Okay, so let's see. I have some mass. I reach some height. What is my initial velocity? Can anybody give me any kind of hint here? What do we think we need to do? I think we need to look at our 2D motion. Look at our equations. That's what I think we need to do. So we know that our shell, okay, is fired straight up. So it goes straight up and it reaches some height and then comes back down, right? Okay, that's a very poor drawing, I'm sorry. But the idea is we have this kind of like free fall from here, right? We know that up at the top here, our velocity in our y direction is 0 meters per second, okay? All right, so from that information, we can say, okay, well, let me look at my equations and I can figure out my initial velocity. Okay, so my initial velocity is in this equation, it's in this one, and this one. Okay, it's in all of these ones. We also know our final velocity, right? Well, we can compare it to, which is way up at the top here. And that's this one here. That's this one. It's not in that one, it's in this one. Excuse me. We don't know any time. We have no idea how long it takes to get up there. So those two are out. So we're left with this bottom equation here. Okay, we do have our height difference. So I'm going to go ahead and use that equation. Vy squared, this is killing me. Vy squared equals V naught y squared minus 2 times g, and then this is going to be y minus y naught. Okay, this y minus y naught is also our height, right, that we just defined up here. And we know our g. Our y naught is 0, okay? And then we can solve for this value here. So v naught y squared is then going to be, because again, this is 0, given this, okay? That is going to be equal to 2 times 9 point, come on, I'm pushing really hard too. 9.8 meters per second squared times our height, which is 110 meters. Okay. So then multiply this out and take the square root, and we have our initial velocity. Okay. And you can check your units, and it'll be in meters per second because we're taking that square root to both sides. Okay. So we'll be left with in meters per second, which is good. Okay. So that means we know how to do that first part. Okay, so that was part A. All right, let me get, nope, that's not what I wanted. What did I want? Okay, now it works. Okay. Silly things that you have to do with this. All right. The next part is asking the mortar itself is a tube that's 0.45 meters long, and it's asking to calculate the average acceleration of the shell in the tube as it goes from 0 to the velocity found in part A. Okay, so let's see. We have some length. We can call that, what can we call that? I'm just going to call it L for a second here. 0.45 meters. And we're firing it straight up, so this must be in the Y direction. If we're firing something straight up, right? Okay. And we want to calculate the average acceleration. So let's see. Well, this isn't going to help now. Actually, where is that other? Do I not have that in here? Nope. Give me a second here. I think I need more equations. Because we really are just working in one dimension right now, right? We're just working in the Y dimension. Okay. Go away. Okay. Oh. As a function of time. Okay, so let's see. Calculate the average acceleration of the shell if the tube is that long. We don't have any time to work with. Initial velocity to final velocity. Oh, it's staring at me. Okay, so we'll use this last equation here to figure this out. Okay, so this part, ignore that it says x, that's just any kind of displacement, right? So our displacement in our case here is that 0.45. Okay, and we can also call that like, oops, we can also call that like delta y. Okay, it's just some displacement. Okay, so we'll use this final equation here. So my velocity, my final velocity, I should say, is going to be equal to my initial velocity squared plus or 2 times some acceleration, which we are trying to find, times our delta y or delta x. Again, just some displacement. Okay. So what I'll do is I will say, okay, my velocity went from 0 to the velocity found in part A. So this initial velocity is when it's just coming out of that tube, okay? So out of tube, I'll say. And then this one is going to be like from the barrel, I guess, from the very start or beginning of that tube. Of tube. Okay. And we're setting that equal to 0 because of what this says. Okay. And then this one is now going to be our V naught Y from A. I'll just write that down. Okay. So then we plug in all of our values. So a lot of times the hardest part about these problems is getting started and figuring out what equations we need to use. So you could probably tell that I was like, oh shoot, which equation? You know, I was kind of confused. But then after some time you find it and you're like, oh, okay. And then you just do some quick algebra after that. Okay, so I'm going to start plugging in values. So, oh, I guess I can't really, but I would plug in my V naught Y from A here, square it. This one is going to be 0. Okay, plus 2A, which is what we're looking for, that A value, my acceleration, and then times my 0.45 meters. Okay. And so you'll do some algebra and solve for A. So let me go ahead and say it's going to be V naught Y squared divided by 2 times 0.45 meters, and that is going to equal my acceleration. Okay. Okay. And again, this is the acceleration just in that tube from starting point to ending point. So if I have some tube, okay, it's from here to the end there. Okay, that's my acceleration. Okay. All right, and again, if you didn't follow, this will be on Canvas, probably later today. Okay, as long as I can upload this video quick enough. Okay. So part C, it says, what is the average force on the shell in the mortar? Okay, and so all you're doing here now, we're finding some force, and remember force is equal to mass times acceleration. And so that's all we're going to do. We're going to take our mass that was given to us, that 2.5 kilograms. Oops. And we're going to multiply it by our acceleration that we found here, found in part B. Okay. And it says that you want to express your answer in newtons. Okay. So, and as a ratio of the weight of the shell. Okay, well, oops. Let's hold on to that part. So calculating it in newtons, again, newtons is kilograms, kilograms times meters per second squared. That's what 1 Newton is. So as long as you calculate this, you should get your answer in newtons. Okay. We haven't been working with any kind of funky units in this portion. So we should be fine there. Then it says express it as a ratio of the weight of the shell. Okay. Well, um, so after finding our force, okay, so that's good. We want to know now the weight of the shell. Now, weight is just a force, okay, and it is going to be our mass of our shell times my acceleration due to gravity. Okay, so this is going to be g. Okay, so that's what you'll do to calculate your force, or I'm sorry, your weight of the shell. Should write that here. Okay, so you'll plug in your numbers here. So 2.5 kilograms and 9.8 meters per second squared, right? Get your weight. I'm going to just call it W. That way we know, okay, that it's the weight. And it says it wants a ratio, so just divide the two, okay? So divide your weight and your force, and then find some ratio, okay? And it may not be a whole number, but all you got to do is divide them. So my ratio will be, no, I want the first one, the other one first. Whoops. My force over my weight. Okay, so that's all you'll do for that last part. Okay, so again, I think the hardest part of this problem is that we had to find which equations to use, and it kind of had you backtrack to other portions of this class. Okay, so that's the hardest part in this one. And that may happen throughout the homework as well. So this was number 11. Okay. All right, any other specific questions regards to the homework? Again, this will be on Canvas. We can even talk about the lecture if something was confusing, or one of these. I know this one is kind of all over the place.
Eric said number 7.
Oh, is it in the chat? Sorry.
Yeah.
The chat is so hard. Okay, so number 7. Okay. Let me move this over. Whoops. Okay. So, okay. Number 7. We have two children pushing horizontally in opposite directions on a third child in a wagon. So this is how I imagine the problem. So this is the wagon and child. Okay, I'm just going to represent it as a box, which is totally fine. And I have children that are pushing in opposite directions on this wagon and child. Okay. And the first child, which I'm going to put over here, F1, is exerting some force of 82 newtons. Okay, so I'm just going to write that down there. F1 equals 82 newtons. And then the second force is from the other child, F2, which is exerting 68 newtons. Then we have some friction. Okay, so I'm going to just label that as F, 13 newtons. And then we have some mass, which is the child and wagon together. That mass is 26 kilograms. Okay. So one of the main things we need to first figure out is which direction our friction is going in. Okay, so let's first look at our little diagram that I just made. So my first force is being applied to the right. Okay, my second force is being applied to the left. And if you notice by our numbers, okay, this force is larger than this force. Okay, so F1 is larger than F2, right? We know that. So our opposing force, or our frictional force, must be trying to oppose that larger force. Okay, so that is the first thing that we need to kind of figure out. Okay, so let's see. The first question is, what is the system of interest if we are wondering about the acceleration of the child in the wagon? So our system of interest would be then that child and wagon. Okay, so for A, it would be the child and the wagon together. That's going to be our system of interest. Okay, now if we draw a free body diagram of everything, we are going to have something like this, but we need a little bit more. Okay, so we have our wagon, we have our frictional force, we have our F1, F2, but we also know that there's some mass to this guy, right? The kid and the wagon. So we know that there's some kind of force due to gravity, right? From that to the ground, right? There's some kind of weight, basically. So we could also label that as weight, whichever you'd prefer. And then we also have some normal force that is exactly the opposite. Okay, I can label it as N or F sub N, whichever you'd prefer. Okay, just be clear in your diagrams, but whichever works for you. Same thing with your weight. Okay, so this is gonna basically be your diagram, okay, your free body diagram. You could also draw it, let me show you. You can also draw it in like your X and your Y direction. So let's see, if I have a plot here, okay, and I want to translate this into this, okay, I have first my F1, I'm going to draw it in black, my F1, and that's along the x-axis, positive x, so I'm going to draw that here, so that's F1. Okay, my F2 is in the opposite direction, but it's not quite equal, so I'm going to draw it a little smaller. So that's F2. I also have my frictional force, which is just little f. Okay, so that's going to be everything on my x-axis. Then I want to draw everything on my y-axis. First thing is my weight. So I'm going to draw that here. I'm going to label that W. And then my normal force, which is going to be in the positive y direction and exactly opposite and equal of W. Equal and opposite, my normal force. Okay. So this is now my free body diagram here. Okay. And this might be a little bit easier to look at because now everything's on an X or Y axis. Okay. Okay. So now we want to know the acceleration of the child in the wagon. Okay, and this is where it might be a little bit confusing or complex. So we want to add up all of our forces. And when we're looking at the acceleration, we want to know, is it in the y-axis or the x-axis? So what are we going after? What are we looking at? Well, if we look at our diagram again, okay, we have our weight due to gravity, right? And we have our normal force. And I said that those were equal and opposite. So that means the acceleration is probably not in our y-axis then, since it's not moving, right? So let's look at our x-axis. Our x-axis, we have a force in the positive x direction of 82 newtons, and then we have one in the negative x direction of 68 newtons, and then another force, a frictional force with 13 newtons, and again that's in our negative x direction. Okay, so we want to know the total acceleration of that system. Okay, stop me if I'm not making any sense. I'm trying to explain it to where it's not super confusing. Okay, so we want to add up all of our forces, basically. That's going to be our first step. We want to know what is going on in that x-axis. Okay, so we're going to ignore the y-axis for now. So I'm going to write down looking only at x-axis. Okay, we want to add up all of our forces. So our F net, right, our total forces will be a positive F1 because that's in our positive x direction. Then we have a negative F2 because it's going in the negative x direction, right? And then a negative small f, which is my frictional force, okay? And all of that should equal what? What should that equal? It should equal some kind of mass times some kind of acceleration. And there must be some acceleration if it's moving, but we'll have to figure that out. So if this, let me just give you a scenario. If this whole thing gives us 0, that means that the F net is 0, right? The total force is 0, meaning that object isn't moving. Okay, so that means that our acceleration had to have been 0 since mass can't equal 0, right? Because we already know that there's some sort of mass here. Okay, maybe that was kind of a confusing comment. Whoops. But let me just go ahead and move on. So we have our positive F1, which I labeled to be 82. So I'm going to go ahead and plug these numbers in. 82 newtons minus F2, 68 newtons. And then my frictional force, 13 newtons. And that equals our mass, which is what? 26 kilograms times my acceleration. Okay, so now this is what we have. So what we will do is add these values up and then solve for my acceleration. So I'm going to go ahead and do that. So 82 minus 68 minus 13. Oh, wow, really? I got 1 Newton. Did I do that right? 82, 68, 13. Okay. Equals 26 kilograms times my acceleration. So my acceleration is, so that divided by 26 is 0.0 0.38 meters per second squared. Okay, so this is now my acceleration in the x direction. In x direction. I'm just going to write that. Okay. Okay, so this is, again, my acceleration of the child in that wagon. Okay. Now, so this all makes sense. Now I have part D. It says, what if the acceleration, what would the acceleration be if friction was a different value? So friction now was 17 newtons. Okay, so I would have the same exact setup. Everything's the same except for my value of friction. Okay, so let's see. 82 newtons minus 68 newtons minus my new friction, which is 17 newtons. Okay, so let's go ahead and get that. Okay, so this is where I'm gonna stop. We have -3 newtons on this side. Okay, and then this will be the same, the 26 times acceleration. Okay, so what I want you to notice here is that now my acceleration, my net force on this side is negative. Okay, you can also say that your acceleration is going to be negative. Okay, because after we divide by this, we're not going to get rid of that negative there, right? It's still going to be there. So now we have some negative acceleration. What does that mean? That just means that it's going in the opposite direction, right? So I set my friction force going this way, right? That's where my friction force is. Frictional force, sorry. And so now my acceleration is, let's see. So my acceleration was first going in this direction. Let me get a different pen color. Maybe black, red. So my acceleration was going in this direction. Okay. From the first portion, part C. But when I changed my frictional force, it actually overcame this one and now going in this direction as well. So basically that frictional force acted, opposite of my first force, F1, and is now going in the negative x direction. Okay, so this is from part D. And this is from part C. Okay, so just noticing that difference. Again, it's just a change in direction. Okay. All right, so hopefully that helped with that one. Again, these problems seem so out there, and then you kind of have to like break them down, and it really helps. Was there any other one that you want to do real quick, or any other questions about the class? I have the chat up, so now I can see if anybody chats me. It doesn't give you any notification. That's what I don't like about Zoom. It doesn't tell you, oh, somebody's in the chat. It doesn't tell you anything. Okay. All right. Well, if there's no more questions on the homework, then let's see. modules. I have almost everything up here. I did notice in the progress quiz for this week, I put in a question about friction and frictional coefficients, which I haven't talked about yet. So I wanted to, or I will probably today make a short little video of basically this chapter 5, but it's really what we've already been looking at. So we've already been looking at friction and such. So I wasn't planning on going over it, but then I'm like, oh, frictional coefficients. So it's real simple. It seems complicated, but really it's just looking at this little table and understanding how to read it and then plugging in numbers. So it's not a huge deal. There might be like one of these on the exam, and there's only one question on the quiz this week, but it's not a huge deal. You just got to know how to look at this table here and use this equation. It's really just multiplying some kind of magnitude here by whatever your force is. That's really it. It's not a huge deal. So watch out for that. I'll probably do that today, a short little video about this, but I don't plan on going into like a huge amount of detail with it. And then next week, or hopefully by the end of this week, I will have up a study guide for you guys for the exam coming up next week. Probably be Friday, next Friday, I mean, for the exam. I'm not quite sure on that yet. That's probably when it'll be. And until then, if you guys have any questions, of course, email me. Or even start a little chat thing on here on Canvas. I think you guys can post questions and announcements. I think I've seen someone do that. Okay, maybe not. I thought I did. Huh. There's got to be some way for you guys to like reach out. Oh, a discussion. I bet that's what it was. You can add a discussion. Like I saw one person do it, asking about lab or something. So you guys can always do that if you need to ask group mates, or not group mates, but classmates anything. Or if they want to start a study session or something with each other, feel free to. Okay. Anyway, I guess that'll do it for this time. And so I will have this recording up as soon as I can. Like I said, YouTube takes a while to upload them. So just bear with me for that. But thanks for coming. I appreciate it. And I will see you next time, hopefully. All right. Have a good one.